Number two, they said, well, then the universe was hot, right? So where did the heat go? It's still here. So they said the universe should be filled with the heat radiation of the Big Bang. And in 1948, they published their paper, and they got the temperature of about 5 degrees Kelvin, 5 degrees above absolute zero, which turns out to be pretty close to the measurement we got, which is 2.7. So they got that based on a few bits of elementary nuclear physics, the lifetime of the neutron, and a few other things. So they said, well, somebody should try to measure this. But in 1948, there were an awful lot of easier things to do, and so nobody really tried. So it was finally discovered in 1965 at Bell Labs in New Jersey by people who were not looking for it. They had built a telemetry antenna to work with the Telstar mission, and they were astronomers too, so they were trying to be very careful. And they were really wonderful engineers, and they said, this radio that we've built makes too much static. This is noise that should not be there. Where is it coming from? So they finally figured out that it must be coming from the sky. It could not be coming from the apparatus. They tried cleaning out the pigeon poop from the antenna, and it was still there. So, okay, they made their discovery. So they didn't know what it was. They had not remembered or were not aware of the predictions that had been made almost 2 decades before. So just down the road from them at Princeton University was a small group that was setting off to go build an apparatus to measure it. They were also not fully aware of the predictions, but they had a new prediction they were going to test. And their story was, well, the universe is bouncing. It's gone out and come back in and bounced. So the cosmic background heat radiation should come from the bouncing universe. So they were looking for it, but they hadn't finished the apparatus. So another astronomer made the connection between these two groups. And so suddenly this was understood, and papers were submitted to the Astrophysical Journal, and in a little while it was in the front page of the New York Times. At which point the people who had discovered it, who really didn't quite feel convinced that it was cosmic, suddenly they had to believe. Because the editor of Physics Today, a Physical Review, sent the paper to the New York Times and explained why it was important. So are we getting closer? Oh, is that one working? Okay. So that one's working. We'll just wait a second until we can all see it. Thank you very much. That was harder work than we thought. Okay. So, so now we're talking about the predicted hot heat from the Big Bang. It was measured, just one brightness at one wavelength was measured, but it turned out to be about 3 degrees above absolute zero, as the guys in 1948 had said. So now we have not only the predicted expansion, but also the helium abundance, and now the temperature of the Big Bang radiation. So now beginning to understand maybe this Big Bang story is really a right story. People didn't know before. They said it could have been quite different. It could have been extremely different, but it wasn't. So, okay, so it's about time to start playing with the picture. So something that I forgot to tell you as I was waving my arms is when you look in the mirror in the morning, you can do a little bit of cosmology. Because where did those atoms come from? I was mumbling earlier that the hydrogen and helium came from the Big Bang. We're not made of hydrogen and helium. Where did the rest of the atoms come from? They came from stars that blew up. So we are totally recycled. Our atoms have been inside stars and they have come back out again. And they may have actually escaped from the galaxy before coming back in to form a new generation of stars and planets. So if you had explained to Aristotle that the atoms came from stars, and that we came around to be made out of those atoms, he would have been pretty amazed. But he might have believed us, because we would have shown him the evidence. Okay, so this little picture tells us that we can look back in time when we look at things that are far away, because we look at things as they were when they sent light to us. So we are actually the only professors who can look back in time, really. See things as they really were. Now, the penalty for us as scientists is we get a pretty blurry view. We can see the sun as it was 500 seconds ago. If you want to look at the edge of the universe, almost all the way back, it's really blurry. So you can only do a lot of measuring and thinking. But we really do see things as they were. So just a little sketch to say we really do it the way you learned in high school to measure distances. If you took trigonometry and geometry, You draw triangles, you measure one side of a triangle and two angles, and you know the shape of the triangle. So this is surveying. So astronomers do it too. But when things are too far away for you to draw the triangle, you use light. You say, well, light gets fainter when the thing is farther away, so that tells us relative distances. And that's what Hubble was doing with the blinking lights. The ones that are close are brighter than the ones far away. So we can tell distances that way. So this is Hubble's chart showing the story that I told you earlier about the galaxies. The farther away, the faster. And this was a puzzle, by the way, in the 1920s, because you divide the distance by the time you get the age of the universe. It looks like it's young compared to the Earth. We're beginning to learn how to measure the age of the Earth back then from radioisotopes. We think the Earth is 4.5 billion years old now, and when Hubble measured this, he got about 2 billion for the age of the universe. Clearly a problem here. It turned out his distance measurements to the Andromeda Nebula were incorrect because those blinking lights out there are a different kind from the ones that are close up. So he didn't know that. Here are pictures of the people I was telling you about. On the left is Alexander Friedmann, the mathematician in Leningrad, who didn't get to find out that he was right. In the middle, little Albert Einstein with Georges Lemaitre. I guess they were friends afterwards, a little better. And Gamow in the upper right corner, and the two young fellows in the lower left are Alpha and Hermann, and that's what they looked like when they came to the launch of our satellite mission, which tested their prediction so well. Another wild story that comes from the Hubbles Law is that although you can look and look and look, Hubbles Law does not allow you to think that you're in the middle. Because you can calculate what the other astronomers on other galaxies would see, and they would say the same thing that we say. Everything looks like it's going away from us. So all of us, we think we're in the middle, so the conclusion is there's not really a middle. And astronomers have been looking for a long time to see if there's one place over there that looks different from another one. And the answer is, if you look far away, they're all the same. So no center, no edge that we can find. Not to say there isn't one, but it's not something we can find. It means they can also not draw you a picture, because you cannot stand outside the universe looking in. We need a higher number of dimensions to be able to do that, and, we can only imagine. So you can now say, well, okay, my universe has never been expanding. My solar system is probably the same as it's been for billions of years. We don't feel this expansionary force. How is this going on? Well, the story is that if some region of the early material was a little more dense than average, it's got enough gravity to stop the expansion. It pulls itself back in against the expansion, so stars and galaxies can all form because gravity reaches across space and pulls things back in. But only if it's strong enough, only if that region is more dense than average. So then after it's all working, then the stars produce the chemical elements, and planets can be formed from the debris, and now we can have the sun releasing nuclear energy for 4.5 billion years and support the development of complexity here on the surface of the Earth, which is a completely amazing phenomenon we have a few ideas about, but it's pretty unexplained so far. So I've got a little summary story about the history of the universe on this chart, and I guess it's kind of little for you to see, so maybe word pictures are even better. But in the upper left, we've got a map of the Big Bang, as seen from here, as measured by the satellite that I worked on, the Cosmic Background Explorer satellite. We've got a story that says galaxies were formed from little things that merged together, like streams flowing together to make great rivers. We've got a picture in the lower left of the Andromeda Nebula, this nearest big one to us. It has two little satellite galaxies that are in the process of falling in. In the upper right, I say a few words. The Big Bang was renamed in the Calvin and Hobbes cartoon strip a few years back, and they said it should be called the Horrendous Space Kablooey. And I like that better, because Big Bang conveys an incorrect idea. It conveys the incorrect idea that we have a little grenade here that goes off at a place. And this allows you to think differently. It says, well, maybe all of space is involved, and that's actually the science story that we have. All of space is involved, and maybe it's even the space itself might be expanding. But we don't know what that means, because space isn't a substance that we know of. Maybe we'll know more after the Nobel Prize announcement of today is better understood. But right now, we don't know what space is or time is. We only know how to measure them. So anyway, then time goes on. The universe cools off, stars are formed, galaxies are formed, The universe becomes transparent at a certain time, so the heat radiation that was there in the original explosion, horrendous space kablooey, is now free to travel immense distances across space. So that's how it is that we can now make a map of it. The universe became transparent, and we can see it was at that moment. So then time goes on, and things happen. And at the bottom of the chart here, I said, well, 5 billion years ago, the universe started accelerating. And that's what the Nobel Prize announcement of today is about. I'll show you more in a bit. So a little bit about the history of the Earth. We haven't actually been sitting here quietly all 4.5 billion years. It has been changing. I guess you all know that the planet, the continents have been drifting around, the temperature has been changing, the chemistry has been changing. But you might not have heard that the solar system itself may not have been stable all this time. When Newton announced that he knew how to calculate orbits, people said, oh, golly, clockwork universe, everything's totally deterministic. We understand everything. Well, that was wrong. The solar system is not necessarily stable. It probably wasn't formed in the configuration it has now. Planets came close to collisions. They may have ejected some out into outer space. Some probably fell into the sun. And I have a little movie to show you about what the early solar system might have been like. So what we have on this chart are 4 inner circles and then a whole lot of green rocks out there. Those are comets and asteroids circulating in the outer solar system around the 4 giant planets. And the simulation says, well, so what if we take off early solar system and we let it run? And after about 700 or 800 million years, it suddenly goes unstable. And this thing that people thought was just like clockwork, it isn't like clockwork. It goes off the rails. The planets start switching their positions, interchanging, and at a certain moment, you'll see the little green rocks go flying everywhere. And a lot of them hit the Earth. This is a period of time we call the late heavy bombardment. And it's a time when life, if it had already existed, would surely have been wiped out because it was really hot and nasty here for a while. It's called the Hadean period in geology, for a good reason. Anyway, yeah, it's done it there, right? So at the end of that, all the rocks are gone. Well, almost. We still are afraid of a few of them that might come to get us. So in the future, what's going to happen? A few things. Oh, welcome. A couple of years ago, in 2009, we celebrated 400 years of telescopic astronomy. Next year, 2012, some people think the Mayan calendar is coming to an end, so will the Earth. I think if the Mayan astronomer were here today, he'd say, we better add another digit. So I think they would have understood. In our future, well, we clearly know that our planet is changing because we're doing things to it. It was changing anyway, but we're making it faster. So after a little while, things will happen. We used to talk about the balance of nature. I think the lesson of modern science is there is no such thing. There's constant competition and change. And so what they told me in 9th grade biology was incorrect. So in about 1 billion years, it'll get too hot here. The sun is getting brighter and brighter and brighter, and we will not be able to live here no matter what we do. In about 5 billion years, the sun expands to the size of the Earth's orbit, and we're actually orbiting inside the surface of the sun, and that's really bad for us. Not that we'll still be here, but anyway, it's really bad. Then the sun will collapse down to a small white dwarf star about the size of what the Earth, I guess, similar in size. So after the sun goes out, the universe continues to expand, and eventually all the stars go out. It'll be dark. So this is a more fun time to be an astronomer. I forgot to mention that in a few billion years, that beautiful Andromeda Nebula is coming toward us, and we will have the collision of galaxies. And it'll be a fun time to watch that, too. We don't actually know whether we're expecting a head-on collision or a glancing blow on the side, and we know what to do to measure, but we can't do it yet. So just a little bit about the reason I have a pin on my lapel. We built beginning in 1974, we started building this satellite at NASA. I was 28 years old when we started this thing, and this is my thesis project grown up into something a lot bigger and more accurate. My thesis project actually failed. Anyway, we wanted to measure this primordial heat radiation, and so this is the instrument we built at Goddard Space Flight Center. And my friend John Wood here, that's with us today, was part of that project.